421 part 1. We're going to talk about some pretty cool stuff. We'll talk about if we made a mistake and there's some issues with the outlier. And we're also going to end up by the end talking about the residual plot, which is kind of interesting. So we're going to break this lesson into two parts. So it says in this lesson you will create residual plots that help you visually determine how well an LSRL fits the data. You will also investigate how outliers affect predictions. So in problem 4.1, you completed an investigation that helped Robbie use a viewing tube to see a football game. Sample data from problem 4.1 is shown in this table. So use your calculator, or we can use Desmos. Let me see what this looks like. Maybe they'll already have it put in for me. Oh, they already made the table for me. God bless them. Okay, so use your calculator or eTool to create the LSRL, and to create a scatter plot in the LSRL. What is the equation in the LSRL? All right, so first off, like I said, they've already done this for me, which is very kind of them. They've already gone through, and I wonder if I can copy the whole thing. I was gonna type it all in myself, but looks like they've done that for me. And again, if you guys will recall, the way to add a table is you're going to go in here and just put a table in. So no big deal. You can put your own table in. Once you have that data in, you can write the LSRL by putting Y1. And again, only Y1 because that's the number that we use here. And that has no numerical value. It's just a name, sort of like the first Y list. The tilde lets the Desmos calculator know that you want to do the LSRL. And then we're going to say M for slope, X1 to let them know they're going to use this X1 data, plus B for the Y-intercept. We come up with a few things here. We have the R squared and the R, which we'll definitely talk about more later in the chapter, but obviously the equation is Y equals 0.13373X plus 1.65925 or 952. So obviously we substitute those in for the M and the B values, and if you can see here, they already have that for us. So nice in Desmos. I don't really have to go through the trouble of showing you how to do it in Desmos because they've already done it for me. And I will go ahead and show you how to put it in the calculator. So if you will remember, let me go ahead and set this up. I'll pause for. If you'll remember, in order to put the data in, we needed to go to the table. Well, first of all, we should probably just clear the memory out of hand. So I'll go second memory, and again 712 or reset all RAM reset. I've cleared my RAM, and now I want to go ahead and create a table. I'm sorry, I want to put input data into table. So right down here. So I'm going to choose stat, and then I'm going to. I'm sorry, what am I doing here? My mistake. I'm going to go stat and then edit, and this allows me to put in the L1, L2 data. If you'll recall, my data is all going to be right here, so I can just go ahead and start putting the data in. Again, my preference is to put the X data in first and then the Y data in second, but you can do it, I guess, if you don't mind going back and forth. Now, as I do this data, something I'm going to keep in mind, a couple things. First of all, I need to make sure that my L1 and L2 lists are the same length, which they are. The second thing is, if you'll recall, they actually gave me a checksum. So I don't know if you guys remember how to do the checksum, but the way the checksum works, if I want to check data, I'm going to go stat, and I'm going to choose calc, so I'll move it over to the right. And I can either choose one variable stats and do them one line at a time, or I can do two variable stats and do them at the same time because they are equal length. Again, if they're different lengths, two variable stats won't work. I do want to do L1 and L2. So you can see it adds up to 816 and it adds up to 122.4. So I'll check this over here. 816, 122.4. So it doesn't mean I'm right. Again, this maybe I screwed up and put 71 and 61, and it still adds up to 816, but it's pretty unlikely I made two errors that worked out perfectly exact. So, all right, so we will continue along here. Sorry, I pushed the wrong button. And we want to get the LSRL. So in order to get the LSRL, I'm going to choose stat. I'm going to choose calc. Again, I'm going to choose the fourth one, linear regression AX plus B, so I can just type in 4. I do want L1 and L2 as my list, but again, I can save this form myself automatically. So I'm going to go down to store reg. I'm going to hit vars, move over to y bars. I want to save the function and I want to save it in y1. So I go here and I will calculate. You'll notice again that hopefully I have the same equation. So let's see if I indeed have the same equation. So 1.3373 and 1.65. So I have the same slope and y-intercept. The last thing I want to do is I want to get the scatter plot. And if you'll remember the scatter plot, when I go to graph, nothing is there. Well, it'll actually show whatever I have for y equals. So to show what's in y equals, but it won't show my data that I've plotted here. And the reason is because I need to define my graph. So I'm going to go to second stat plot, and I'm going to turn my graph on, and I want to run L1, L2. Now I can go to graph, and then again I can go to zoom 9, and that will kind of put that data in for me. And hopefully we'll see that, what am I doing? Push the wrong button. Hopefully we'll see that this data looks very similar. And you can see whether I use Desmos and typed it in here with the y tilde mx plus b, or whether I went through the TI-84 process, my data does look the same. So at that, it says, when entering the data in a calculator, Amy accidentally entered 144 and 10.7. So here's what I'm going to do. I'm going to go back over here, and there's a lot going on here, but I'm going to just add this line. I'm going to say y equals, this is my original one with the original data. So you can see that that's my LSRL. Well, what it's telling me to do is it's saying, hey, let's pretend that we had screwed up here, or that we're fixing a screw up, I don't remember which. And we're going to go to 144 10.7. So 144 10.7 instead of 20.7. So I'm going to go here to 10.7. And you can see how much that 1 point screwed up our old LSRL. And here's the new LSRL. So again, the blue one has the data with this new point that was a mistake. And you can see it pulled it way down. And I had just typed in the original LSRL as the 20.7, right? So we can kind of compare the two. It didn't ask me to put this black line in, I just put it in so you could see the impact of how much just changing that by 10 points changes. Again, when I go back to 20.7, it goes right back. And when I go to 10.7, it really drastically switches what's going on there. So we can do the same thing here. I can go stat, edit, and I can change this to 10.7. And I can rerun my LSRL. And one thing that is kind of cool about this is I have L1, L2. I'm going to go down here, I'm going to go vars, y vars, and I'm going to save this function. But instead of saving it in the first spot, I'm going to save it in the second spot. And I'll show you why. Because it's going to give me the new LSRL, I'm sorry, the new equation, the new LSRL, and you can see that they do match. Desmos matches the calculator. But when I go to y equals, I have the original equation and the new one. So when I graph it now, it'll be the original one before I screwed up that data, and then with the outlier, the impact of that outlier, and you can see the impact that it has, and it's pretty dramatic. All right, so make this change to your data, sketch the new point in the LSRL in a different color. Would you consider this point an outlier? I would. It's definitely screwed up. It says, what's the impact of the outlier? Will Amy's predictions for the field of view be too large or too small? Well, here's my prediction line originally, and here's my prediction line now. It looks like it's going to make my prediction too low. I hope you agree with that again. And if you look here again, same thing. It looks like my new prediction will be too low now that I've screwed that 1 point up. All right, so some interesting conversations so far. Now it says Julia's father would like to open a restaurant and is deciding how much to charge for the toppings on the pizza. He sent Julia to 8 different restaurants around town to find out how much they charge. Julia returned with the following information. So what I'm going to do here is I'm going to go to Desmos. Again, I have to go through the whole process now. So I'm going to insert a table. You can see I have L1, X1, Y1. And I'm just going to put this data. 1, 3, I'll kind of jot this down as I go. So 1, 3, 4, 6, 3, 5, 0, 2. And then I'm going to have my Y values 10.5, 9, 14, 15, 12.5, 16.5, 8, and 9. So should have that written down already. I apologize, but you can see I'm just putting this data in. And then I will put my Y values in. And if you look over here, you can see that this is kind of what the data looks like. And then I can write my equation. And again, it's y1, and this has no numerical value. I was pointing with my finger at the screen. You couldn't see that. So this has no numerical value. It just references this right here. I need my tilde, so I will go here and put my tilde, mx1 plus b. So there is my equation and data right there. Now I will go and again, don't forget, you should be looking at this, but I'm going to kind of put this aside for the minute because it's just going to help me look here. So the first thing I'm going to do is clear my data. Again, that was 712. Now I'll put the new data in, and I just don't want the two things to get in each other's way. So I'm running all new data. Uh-oh, that was supposed to be a 0, then a 2. And then here I have 10.5, 9, 14, 15, 12.5, 16.5, 8, 9. You can see I will go stat, calc, I will run the linear regression. I will go to vars, y-vars. And again, I just want to make this clear. I'll save it in y1 and I will calculate, and hopefully I'll get the same equation. When I cleared the data, I got rid of that old data from the previous problem. So I have the same slope and the same y-intercept, which we need to make sense of. We haven't discussed what this means yet. I will go to my stat plot. I will turn it on. I want to run L1, L2, so I'll go graph. And again, a nice thing to do here would be just we go zoom 9, and you can see that they look very similar. The scale's a little bit different, but it essentially is the same data. I got my 2 points down here, my 2 points down here, my 4 points up here, my 4 points up here. So the data is essentially the same. So again, whether you want to use Desmos or whether you want to use a TI-84, you should be comfortable using both, quite frankly. All right, so it says, Julia needs you to write a report for her father about what he should charge for a 2-topping pizza. With your team, discuss what elements of the statistical analysis report should contain, and then write your report. So let's go back over here and let's change this paper background so we can discuss this. Actually, I don't know, maybe we should just go here. It's not going to kill us to go there. And our equation is, again, and since I already have the line saved, I don't need to have it saved twice. Oh, are you kidding me? That was brutal. I go through all that and then push the wrong button. Ugh, so frustrating. All right, let's try and be a little more concise this time. So I get the equation y equals 1.35x, or 1.36x is probably better, plus 7.74. So let's go over here and let's write that. Y equals 1.36x plus 774. What does this mean? Well, my slope, of course, is change in y over change in x. So I have 1.36 y's, or dollars, right, over 1 x's for topping. That makes a lot of sense in the context of this problem. I'm going to pay $1.36 for every topping, right? Every extra topping costs me $1.36. And then my y-intercept says 0 toppings, or, you know, I guess a good old-fashioned cheese pizza would cost me $7.74. And that makes a lot of sense. Again, $7.74 for a cheese pizza, $1.36 for each topping. That's the average. So if I wanted to have 2 toppings, I would go here and I would say, all right, well, I'm going to say $1.36 times 2 plus 774. It would make a lot of sense if it was $10.46. So a 2-topping pizza would be $10.46. So let me go ahead and kind of go back over here because there's a couple things I might want to talk about that the book might not be. So it doesn't ask us to run the residuals on this at all in any way, shape, or form. But let's go back and just look at the scatter plot of these. What does it mean when we have a negative residual and a positive residual? And again, a positive residual means it's more than we expected, and a negative residual means it's less than we expected, right? This is our expectation right here. So what that means is this pizza costs almost exactly what we would have predicted, but this pizza costs less than we predicted. This pizza costs less than we predicted. These cost more. So in this example, I would say this is your cheapest pizza, right? You're a high school guy with your buddies. This is probably the one you're going to pick right here. You're getting a lot of calories for the price. This one right here, it's probably the most expensive pizza. Maybe it's got better ingredients. Maybe it's got a tablecloth setting, and it's the fanciest restaurant of them. But again, it didn't really ask us about the residuals, but I just wanted to point that out. That pizza right there is what we expect to pay. This one's cheaper than we expected to pay by the most. This one is the most we expected to pay by the most. Again, not saying it's not good value, just saying that's what it costs. So we're going to look at something called the residual plot. We're going to introduce it today, and or I should say in this lesson, and then I'm going to make the next lesson immediately, but in theory that'll be the next day's lesson, for what a residual plot is, how you make it. So a residual plot can help you determine if a linear model is a good fit for a scatter plot of data. Whenever an LSRL is drawn on a scatter plot, a residual plot can be made, can also be created. A residual plot has an x-axis that is the same as the scatter plot, and the y-axis is the residuals. So what that means is this, that when I look at this graph of this, or if I look at the graph here, the x-axis is the same, but what's different is instead of your outputs, your residuals are going to be what's the difference. So a poor man's residual plot essentially turns this thing so that this line is parallel or is horizontal, and I can't really do that, but you can see I have one slightly above, one above, below, below, above, above, above. So again, if you turn this thing sideways, is what it would look like, and unfortunately I don't really have the capabilities of sort of rotating anything here, which is unfortunate. It would be super helpful if I did. So what does that mean? Well, that means if I want to match these things up here, and it would probably make more sense for me to go ahead and close this and open a new one. So I will open up 422b. What we're saying is, oh shoot, I guess I still am on 422a, my mistake. Well, now I really wish I'd paused this video. Okay, so if I look, I guess I never actually saved it. Let me pause this and figure out what I'm looking for, please. If anyone ever watched this video, obviously what happened was I was opening 422 instead of 421. And then, by the way, I needed C instead of B, so it's good I eventually paused the video. So long story short, they want us to match the scatter plot. And remember, this is the X and this is the Y. This is the X and this is the Y. This is the X and the Y versus the residual, right? So a scatter plot has the X is the same, but the residual is different. Well, what does that mean? Well, think about it. My residual here is barely above, and my residual here is barely below. That doesn't look like this. It doesn't look like this, but it does look like this, right? Barely above, barely below, then two barely above. There's two barely above, and then I have kind of two above and two below all together. There we go right there. And then below, and then I got kind of this arc thing. So I think I think 1 and C go together. So 1 and C go together. I hope you see what I'm saying. Now let's look at this scatter plot. Well, this scatter plot, I immediately have on the left side a 1 above and 1 below, and they're both pretty far apart. Well, this one has 3. So this is probably a better example. 1 above, 1 below. You can see that I kind of have a cluster in the middle, kind of stretches out a little bit. At the end, I have 2 above and 1 below. There's my 2 above and 1 below. So I think 2 and B go together as well. And then the last one, obviously, I mean, clearly 3 is going to go with A, but let's at least talk about it. There we go. 1 above, 1 barely above, 1 below. 1 above, 1 barely above, 1 barely below. 1 above, 1 barely below, 1 above, 1 barely below. So you can see, if you just sort of turn your head sideways to make this go horizontal and rotate it, you get the residual plot. So it says, for which of these scatter plots does a linear model fit the data best? How does a residual plot help you make that decision? So let's talk about a residual plot is and what it does. So a residual plot essentially just says this. Is there a pattern? Is there a pattern to what I'm seeing? So imagine if we saw this. Let me go ahead and let me exaggerate this greatly. So let's say we had this data, right? And the data looked like this. And it said, and we told the calculator, hey, draw a line through that. Because if we tell the calculator to draw a line, it's going to draw a line. The calculator's not going to turn around and say, well, geez, I think a curve would have been better than a line. It asked us to draw a line, so we did. So now what would this residual plot look like? Well, this residual plot, and I hope we can recognize it for what we're talking about here, our residual plot would look like this. Again, this line would get turned horizontal. I would have a couple above, these ones, and then I have a bunch below, and then I would have a couple above. So my question is, do you see a pattern here? I do. Right? There's definitely a pattern. It starts below, starts above, goes below, goes back above. So if there's a pattern, is a line a good fit? That means, actually, I guess I should have said, then it's not a line. So what we're going to have here is something that says if there's a pattern in the residual plot, it's no line. Right? No line. But if there's no pattern, then we think a line is probably a good fit. And it's the opposite of what everybody always thinks. But again, let's go back to our examples and let's talk about why that would be the case. So if I go here, oh, there we go. Okay, so if I look at these, are you seeing a pattern in this residual plot? I would argue yes. So I would say a line was not a good fit for this. And I hope you can see that a curve probably would have been a better fit, right? So I don't think this should be a line. We'll put no line because we do see a pattern. And again, pattern equals no line. So what about this one? Do we see a pattern here? I would say no. I'm not really seeing much of a pattern here, right? If it's to the left, it could be above or below. If it's in the middle, it could be above or below. If it's to the right, it could be above or below. So in that case, I would say no pattern. So I think a line's a good fit. And again, I think that went with this one, right? So no pattern. I think a line is a good fit. Now, what about this one? Well, I guess you could argue and say, well, it could be above or below to the left and it could be above or below to the right. But if you think about it, I definitely see a pattern there, right? I mean, if you told me, oh, the input is on the low end, I would say, oh, yeah, my prediction's good. If you told me my input's on the high end, I would say, oh, my prediction becomes much less reliable. So I would say here, I definitely see a pattern. And again, I would say no line. And I hope you see that same thing here. You see how it sort of sprays as it goes. So again, here I would say pattern equals no line. And again, just to kind of reiterate which ones go together, and maybe I should change the colors here. Those ones go together, those ones go together, and those ones go together. And I hope that all makes sense as to why when there's no pattern, a line makes sense. When there is a pattern, a line doesn't make sense. And what the residual plot does. The residual plot just helps us understand if we even think we should have drawn a line in the first place. Maybe we go through all the data and we get this equation and we use our LSRL, right? We go through all these steps. We go through all these steps and we get our LSRL, and then at the end we find out we shouldn't have even have used a line in the first place, that it should have been a curve or something else all along.